What I have depicted right over here is a fairly typical Sn2 reaction. We see this hydroxide. It substitutes this bromine. It becomes a hydroxyl group. The bromine so it gives this pair to form this bond. Then this bond and both of those electrons go to the bromine, and now that becomes the bromide anion. So we've seen this multiple times. But what I want to really study in this video is what happens to the handedness of these molecules, or to this molecule right over here. I guess you could say to the substrate, although obviously one group gets substituted with another. So let's name this thing right over here. So if we start counting at this carbon, 1, 2, 3, 4. 4-carbon backbone. It is all single bonds. This is a butane. This is a butane. And then it has a bromine at the number 2 carbon. So this is 2-bromobutane. So let me write this. 2-bromobutane. And then after this reaction, it becomes, so once again, we still have 4 carbons. But now, instead of a bromo group, we have a hydroxyl group, which makes this an alcohol. So instead of just calling it butane, we would now call it butanol. Butanol, because of this hydroxyl group right over here. Butanol right over here. And the hydroxyl group is attached to the 1, 2. So this is 1, 2 carbon. So this is 2-butanol. But what I really want to think about is the chirality, or the handedness. And we see here this carbon, in both cases, it is a chiral carbon. The 4 things that it is bonded to are all different. A bromine, a CH3, a hydrogen, and then you could kind of view this as an ethyl group. It's bonded to 2 carbons right over here. So these are all different, so we can think about its handedness. Same here, bonded to 4 different things. So whenever you're thinking about chirality, the convention is take the thing that it's bonded to that has the lowest atomic number and put that in the back. Well, hydrogen has the lowest atomic number out of all of these 4 things, so you can imagine that being put into the back, and in fact, it's already drawn that way, so it's kind of going into the screen. So we'll focus on these 3 things right out here. And the convention is start with the thing that has the highest atomic number, and the thing that has the highest atomic number is the bromine. Out of the 4 things that this chiral carbon is bonded to, and then go in the order, and then rotate in the order of where the next highest atomic number is. Well, you say, well, you have a carbon there, they have the same atomic number, but then you go to what it's bonded to for the tiebreaker. And this is bonded to 3 hydrogens, this is bonded to 2 hydrogens, and then another carbon. So this extra carbon breaks that atomic number tiebreaker, so we go in this direction. Right over here. And the way I think about it is what's happening at the top. Well, we're moving to the right. We are moving in the clockwise directions. So we would call this R2-bromobutane. And we have other videos where we go into much more detail about naming chiral molecules. But I like to think about what's happening at the top. R, my little mnemonic in my head is R for right. R2-bromobutane is right over here. Now let's think about what's going on here. Once again, put the hydrogen in the back. It has the lowest atomic number, and so we'll focus on the carbons and the oxygen. Out of carbons and oxygen, oxygen has the highest atomic number. And then we'll move in the direction of the next highest. Well, once again, the CH2, CH3, the C's have the same atomic number, but then the tiebreaker is when you think about what it's bonded to. This is bonded to another carbon, while this is all hydrogens. So we move in this direction. We move in this direction, or counterclockwise direction, and our chirality naming conventions is we would say S for sinister, S2-butanol. Now the whole reason why I went through this exercise is to show you that in this SN2 reaction, the handedness, the chirality has changed for the molecule. You can imagine that if you imagine that over here, this 2-bromobutane, if this was an umbrella where the bromine is kind of the handle and this is kind of an upward turned umbrella, all of a sudden the nucleophile comes in, the leaving group pops off, and then the umbrella pops off, or the umbrella goes in the other direction. It has kind of changed because the nucleophile is coming from the left side, the leaving group is leaving from the right. It has changed its handedness. And the reason why this is interesting is, well, because in an SN2 reaction, this now changed. I went from R to S. In an SN1 reaction, as we'll see, because in SN1 reaction, the nucleophile leaves on its own, and then the leaving group leaves on its own, and then the nucleophile comes in, and it can come in from any side. So with an SN1 reaction, you get a mix. You might switch handedness, or you might not switch handedness. So the whole point of this video is to get you a little bit more, thinking a little bit more about the stereochemistry and the handedness of SN2 reactions.